Straight and level flight. In a theoretical situation, lift exactly balances weight and thrust balances drag, forming a couple of forces. In straight and level flight, an aircraft is in equilibrium, i.e. the resultant of all the forces acting on the aircraft is zero, and there is no tendency to accelerate or decelerate. The lift-weight and thrust-drag couples balance, and there is no residual pitching moment. For propeller-driven aircraft, power required equals thrust required multiplied by TAS. Note that thrust required will balance drag. The position of the power curve is a function of weight and pressure altitude. For a heavy aircraft, there's a shift up and to the right for the required power curve. At altitude, higher altitude, there's a shift up and to the right of the required power curve. There are characteristic points of the power required curve. One is minimum speed, stall speed. 2 is the speed for minimum required power, the minimum rate of descent speed. 3 is the speed for minimum drag, maximum glide speed. And 4 is the maximum speed theoretically possible. The power available curve for propeller-driven aircraft. The position of the available power curve varies with selected power and pressure altitude. If you select a higher power, there'll be more available power. At lower altitude, sea level, there'll be more available power. As altitude increases, available power decreases. Maximum endurance and range for propeller aircraft. The best endurance is achieved when the least amount of fuel is burnt in a given time, i.e. minimum power. Maximum range is obtained when the highest possible mileage is achieved for a given amount of fuel. Maximum range equals nautical miles divided by burnt fuel, and nautical miles divided by time is knots. Burnt fuel divided by time is a measure of fuel flow. So a maximum amount of knots to fuel flow will equate to maximum range. And a minimum amount of fuel flow to knots, which is another way of saying the same thing, will also equate to maximum range. When you're flying with a minimum fuel flow, this is flying at a minimum required power. Note maximum range speed is higher than speed for maximum endurance. Variation with altitude. Speeds for maximum endurance and maximum range increase with altitude. Jet-driven aircraft. A jet engine produces thrust. Thrust required is necessary to overcome drag. For a heavier aircraft, there is more required thrust, and the thrust required curve or drag curve shifts up and to the right. At altitude, the required thrust shifts to the right. Required thrust is therefore a function of weight and pressure altitude. There are characteristic points of a required thrust curve. 1 is minimum speed, stall speed. 2 is minimum drag speed, it's VMD. 3 is the best ratio between required thrust and speed. And 4 is maximum theoretical speed. Available thrust curves for jets. With a higher N1, that's a higher thrust setting, there'll be more available thrust. At lower altitude, or sea level, there's more available thrust. And with increasing altitude, available thrust decreases. Maximum endurance and range for the jet. For a jet, fuel flow is proportional to thrust produced. Maximum endurance is achieved when fuel flow is lowest, i.e. at the minimum drag speed. Maximum range is achieved at the speed which gives the minimum ratio of required thrust divided by velocity. The speed for maximum endurance is less than the speed for maximum range.